I think let's start. Okay. Any questions from the last lecture? Any questions? No questions, Okay. So some of you asked me about the workshop, asked me about the project. Okay, so I think this term, because Professor Heng is still on medical leave, so the plan is I will start my part 2, okay, until he comes back, okay. So basically, what we'll do is we will, instead of doing part 1 at the beginning, we'll do part 2, okay. The good news is that part 1, part 2 is not very strongly coupled, okay, all right. So we have no choice. We go down this solution, and then regarding projects, right? Regarding projects, the 2 sub projects. Normally, part 1 we have sub project, part 2 sub project. I will discuss with Professor Heng how to handle this, okay? And if needed, I will try and start my sub project first, okay? But now the question is whether you guys are familiar with how to use the simulator, the Cadence software. Okay, how many people here have used Cadence before and know how to use Cadence? Okay, maybe ask, how many people here have not used Cadence before, don't know how to use Cadence? Okay, so a few, okay. So I think the workshop is supposed to help you learn how to use the Cadence part, okay? Anyway, Professor Heng has given you the slides, right? So you all can try, okay? Cadence is the de facto EDA, the electronic design automation tool, okay, for analog people and also for mixed signal. They also offer some things for digital, okay, but definitely for the analog side, they are by far the dominant EDA software. If you go and join any company outside, I think likely they are using Cadence, okay. So it's good to learn how to use Cadence, okay. Meaning what? Meaning how to do a schematic capture, right? How to enter your schematic into the Cadence software, all right? The transistors, the capacitor, resistor, how to connect them all together, and then from there, then you can use their simulation software, how to simulate the circuit, all right? So how many of you have used LT Spice before? LT Spice? Yeah, so Cadence basically is a more powerful version of LT Spice, okay, all right, okay. So if you intend to continue in this area of analog design, you should definitely learn how to use Cadence, okay. I think it's not too difficult to learn, Of course, it has a lot of functionality, all right. But for you guys, the most simplest thing is how to enter the schematic, all right. How to set up the simulation test bench, okay, right? It means if you design your op-amp, all right, then you need to test it, right? Simulate, test it. How to do the simulation? How to connect in all the voltage source? How to probe which point you want to measure, right? Which output, all right? What kind of analysis you want to do, right? Transient, DC operating point, AC small signal, okay? All these are all in the tool, okay? So a lot of things that you do in class, right? This hand analysis, all this, right? Actually, in the working world, people are relying on the tool, okay, on the software to simulate for you, okay. Then of course you ask me, then why we go through EE5507, teach you how to analyze the circuit and all this, okay? That's because you need to understand how the circuit works, all right? And then also you will need to have a double check on the simulation result. Okay? Okay, so by doing this simple analysis, you have a rough idea of what the output result should be. Okay, so sometimes the simulator may got a problem. Okay, the simulator give you a result that's wrong. Okay? And so you have to be able to know, something is wrong here, right? Okay? Okay, so basically that's the long and short of it. So please go through the workshop slides yourself and try. I notice some of you reported some problem, right? Cannot get some plot or this. Okay? So if you have this kind of problem, please send an email. Send email to myself and Professor Heng. Alright? And then he will see how we can help you lah. Okay? If you know of students in, I think, Professor Gerald Yu's group, right? I don't know what group is that. He has a lab group, right? Alright, they also use a lot of these things, so they may be able to help you also. Okay? Unfortunately, this class has got no TA. Okay? Okay, has got no TA. Otherwise, we ask the TA to help. Alright? Okay? But I think previous years, I think not much problem. I think last year we started using Cadence for the first time. Okay, so last year I think some people use LT Spice, some people use Cadence. Okay, right? But yeah, but learning how to use the software is important. Okay. Okay. Let's see. Let me just open up first. Okay, so this was last week's lecture. I made a slight modification, which I will show you all. Okay, so last week we talked about increasing the order of the noise shaper from first to second order. So this is a slide I added, okay? So one way to build a second order noise shaper is to put a single loop and put two integrator inside. Okay? Right? One integrator, two integrator. Put it in a single loop, okay, with feedback. So another way is what we call a cascade circuit, okay? Cascade. Meaning we put one first order, cascade with second first order. Okay? Then we take the two outputs and combine them digitally. Alright? Y1, Y2, combine them digitally. And then if you do the mathematics analyzer, you find that you can also get a second order. You see? The noise is shaped by second order. Alright? So this is what we call a cascade. Alright? You use two first order loop and then we get a cascade. The important thing to realize here is that we do this to cancel the condensation noise of the first stage, E1, okay? E1 is cancelled, all right, by this digital summation circuit. And the cancellation is not perfect because part of it is in the analog side, the combination is in the digital side, okay? So, so there's a problem of some slight mismatch between the analog and digital. Okay, so that's the limitation of this kind of a cascade circuit, right? Okay, but people like it because we know that the first order loop is stable, right? Whereas if we use second, third order single loop, it can become unstable. Okay, right? So the reason why I added this slide is because in your homework number, okay, my part 2 is 4, 5, 6. Professor Heng is 1, 2, 3. Okay, so homework 4 is the first homework that I will give you. It's already been put into Luminous already. Okay, you can take a look at the homework, and there's one part that you need to roughly know about this, the reason why you have a cascade, all this. Okay. Okay, so the homework issued today and is due. Anybody know when it's due? Yeah, okay, so I make sure it's not due on Chinese New Year Eve, okay? Okay, so it's you 2 weeks, you have 2 weeks, okay, on the 7th of February. All right. So normally the homework will be given out on a Monday, all right, and then it will be due either the following Monday or what at 11:59. Okay, all right. Okay. Let me close this. Okay, so today, I think we'll be talking about this topic on filters. All right? Okay? There'll be quite a lot of slides. I may not go through every single slide because this is the one that I combine. 2 lectures from previous years into one. Okay? So as usual, we do a quick review of the previous last week's lecture. All right? We talk about ADC, DAC, the concept, what is the important role in signal processing, and how we measure some of the performance, static, dynamic, INL, DNL, all these things. All right? And then we had a very quick review of the different ADC architectures and what's the different accuracy and speed. And then we spent the remaining time focusing on one type of ADC, which we call the delta sigma ADC. All right? Which is quite commonly used nowadays. And also it illustrates a lot of signal processing concept that's applied in ADC. Okay? All right? So concepts like oversampling, how you use noise, how the quantization noise is shaped, all right, to squeeze out more performance. And then we spent some time talking about how we analyze this thing, okay? And we basically use a linear analysis approximation for the transfer function. Okay? Why is it only an approximation? You know, when we do the algebraic thing, right? Y equals xz minus 1 plus plus the filter function, and then E is the quantized noise. So why is that? Why is it only an approximation? Anybody know? Okay, it's an approximation because the actual circuit is not fully linear. All right? It is not fully linear because of which element? Which element? Which element in the delta sigma circuit is not fully linear? The quantizer, okay? The quantizer is not a linear element. Okay? All right? So the single bit quantizer is just a comparator. Okay? So it only has 2 states, right? Low, high, 0, 1. Okay? All right? So that is a non-linear lah, because the transfer function is like this, up like this. Okay? So it's non-linear. Okay? That's why the actual delta sigma ADC is non-linear, but for our analysis and for our design insight, okay, we treat it as a linear circuit. And from there we get a lot of information. Right? We get a lot of information. Okay? Okay, but today we'll be talking about another different type of circuit. Basically it's a filter, right? Or an active RC filter. Now, what does a filter do? Anybody? What is the function of a filter? Remove harmonics. Okay. Okay, anybody else? What's the function of a filter? Okay, remove unwanted frequency, right? Okay, very good. Okay? Yeah, so basically the filter is that, okay? Okay? You have a signal that you want to pass, okay, to get out. And then everything else that you don't want, okay, we want to get rid of. Okay? So that's the basic purpose of a filter. Now it's just like a water filter, water filter, right? You want the pure water to go through, but all the dirt you want to stop it. Okay? Alright? So in the filter we say about selection. So a filter can select, okay, select certain frequencies. Alright? And then you will reject certain frequencies. So we use terms like pass band. What is a pass band, and what is the stop band or the reject band? Okay, all right. And there are different types of filter, right? Low pass, high pass, band pass, okay, notch, all right. So filters are very useful. They are very useful in signal processing. Okay, because signal processing, you have a signal which is in a certain signal band, all right, which you want to pass, and then there's everything else outside, noise, interference, you want to reject. Okay, all right. So in the early days of signal processing, as I told you, all right, all the circuits were analog, right? Were analog, and therefore a lot of analog filters were used. Okay, but it's different in today's world because of the emergence of digital signal processing, or DSP. Okay, so because of that, a lot of the signal processing is done in the digital domain, right? Of course, the digital side also got filters, right? It's called digital filters, right? So in this situation, where is the analog filter being used? All right, so it's being used in a lot of RF circuits, radio frequency circuits. You need a lot of this kind of signal band selection. Okay, so you need an analog filter there. RF is basically high frequency analog, all right. And then also in a lot of analog circuits, we mentioned about this thing called anti-alias, anti-alias filtering. That means before you do your A to D conversion, all right, you need to isolate the signal band, all right, and get rid of the higher frequency thing, because if they come in, they could cause aliasing in your result. Okay, so AA is anti-aliasing. And then of course, you find that the analog filter is one of the fundamental building blocks in a Taylor signal converter. Okay. Okay. So this topic, analog filter, is actually a very, very well established topic. Okay, it's been around for many years, right? And there's a lot of material. Okay, you know, there are different filter types. Okay, the theory of different filter types. Butterworth, you know, Chebyshev, okay, many different names, okay, right? And why do we have different filter types? Basically, we need to trade off. We need to trade off performance for filter complexity. Okay, what's our performance? Okay, pass band. Okay, what is the ripple on the filter? What is the stop band? How steep is the transition from the pass band to the stop band? Okay, all right. For analysis, okay, there's also a lot of tools available, all right, to help you to analyze the filter. Not only help you analyze the filter, but help you actually to synthesize the filter. Okay, all right. So these are two important terms here now to look at and understand: analysis and synthesis. Okay, so it's good to understand what's the meaning of analysis, what's the meaning of synthesis. Okay, analysis, you all know, right? I give you a circuit, I ask you to analyze this circuit. What does this circuit do? Right, that's analysis. Okay, what is synthesis? Synthesis is I give you some requirement or some spec, and I ask you to design a circuit that will meet these requirements. Okay, all right. So these two things are analysis and synthesis. Okay? So I'll ask you a question. When you use a simulator, is it analysis or synthesis? Sorry? Analysis, right? Okay? Important, huh? Okay? So the simulator only helps you to analyze the circuit. Okay? You must still input the circuit, right? You must still generate the circuit, right? This is a synthesis step, okay? So, as of today, at least there's still, for a lot of analog circuits, it's still being synthesized by a human being, okay? All right? Now, so if I give you some requirements for op-amp, then, you know, you as a designer, you're supposed to design the op-amp. So you must come up with the op-amp. What type of op-amp? What's architecture and all this? Okay? This is the synthesis step. On the digital side, they have a lot of tools now that help them to synthesize. Okay? Of course, the question we ask ourselves is, when will the day come when the computer simulation tool can also synthesize analog circuits? Okay? And the answer is? This guy shake his head. I said no. Okay, so there's research in this area, okay, and there's some progress in this area, okay, but it has not achieved widespread acceptance yet, okay. Because people keep saying, oh, the analog circuit is very complicated. There's a lot of trade-off. So it's not easy for the computer to synthesize for you. Okay. But of course, what I'm thinking is that the reality is that the computer is getting more and more powerful. Okay. And if you read, all these things about artificial intelligence and deep learning and all this sort of thing, right? So I think it will happen. I don't know when, but I think it will happen. Okay? The day that occurred when the computer, all right, beat the world Go, Weiqi, Weiqi, the game Go, right? People also say, well, this game is very complicated, right? It's impossible for the computer to, to beat a human being, right? Then I think a few years ago, right, the AlphaGo, right, came and then, whacked the human player, right? Right? So, so we have to say that the computer is getting more and more powerful. Not only that, it's also getting more and more, I wouldn't use the word intelligent, but it's got some intelligence now. Okay? So, I think it will be a matter of time, before the computer software can also start to synthesize some of these circuits. Okay? But I think hopefully it's not so fast. Okay? Okay. And then I think in the very early days, it was a lot of continuous time filters. Okay? Continuous time filters. Okay? In the S Laplace domain. But now I think increasingly we see a lot of discrete time filters in the Z domain. Right? Okay? So switch capacitors, circuits, all these are discrete time circuits and we analyze the frequency response in the Z domain. Okay? So remember last week I told you all, right? Why is useful for the S domain and the Z domain? Okay, why is the S domain, the plus domain useful? Anybody? Anybody can remember or not? Why when you do circuit analysis in the undergraduate, whatever, they always teach you, right? Laplace domain, right? All these things, right? But why? Is it to make your life complicated? No. Sorry? Okay. Basically, it's to convert time domain integral differential equations, right, into Laplace domain algebraic equations, right? That's one simple way to understand. Okay, so if I give you a circuit, right, with RLC elements, right, ask you to analyze, right? You analyze in a time domain, you will end up with a integral differential equation, because capacitor IC dV dt, inductor V equals L di dt, resistor R equals Ri. So you analyze the circuit, you come up with an integral differential equation. Okay? And those things are not easy to solve. Okay? But if you convert all the elements into the Laplace domain, you can write a simple algebraic equation. Okay? Just map capacitor impedance what in the Laplace domain? What's the impedance of a capacitor in the Laplace domain? 1 over SC, right? Inductor is SL, R is RL, right? Okay? So, yeah, so then you analyze it, you get an output or transfer function in terms of S, okay? And then you can do the inverse Laplace transform to find what is the time domain answer, okay? Right? But the S domain transfer function itself is also useful because from there you can get the frequency response, okay? And later on when we do the filter, you will see, right? How we get the frequency response, okay? All right? Okay. Okay, so basically we are going to talk about different filter types, different filter responses, different specs to specify the filter, and then we will talk about op-amp based I think should be filters. Okay. Okay, so we will start with basically we will talk about first order filter. Okay, first order. Okay, so we talk about filter being frequency selective, okay? And then it will remove unwanted frequency. But actually filter has also a different function where we can just say we don't change the magnitude at all of the signal, but we just want to change the phase, okay? And this is useful for delay equalization, okay? So we preserve the magnitude, we just modify the phase. Okay, so there are, so many different types of filter. Okay, this is the low pass. Low pass means I pass low frequency, I reject high frequency. Okay, high pass, opposite. Okay, pass high frequency, reject low frequency. Band pass, okay, I only pass a band. Band stop is I reject a certain narrow band here. Okay, and the all pass is basically, yeah, you may question, okay, why we need all pass, right? So all pass basically pass everything but change the phase. Okay, all right. Okay, so filters can be implemented, all right, in different ways by different circuits. Okay, so we will not talk about digital filters in this course, but they are of course a different class of filters. But for the analog filters, basically there are at least 3 different types. The active, the passive, and the waveguide. Okay, the passive is basically means that we do not use any active element inside. It means op-amp is an active element. Okay, we only use passive element. All right, resistor, inductor, capacitor. All these are passive elements. Okay, they do not have their own. They do not have power. Okay, they do not generate power. Okay, for active, it means that we can either use an op-amp together with resistor, capacitor. Okay, or we can use what are called GMC filters or transconductor C filters. All right. Okay, later on we'll see what this means. And then of course we can also use switch capacitor filters. All right, switch capacitor filters. If I'm going too fast, let me know, because today a lot of slides, so All right. So basically, how do we analyze the filter? All right, we treat it as a simple 2-port network. Okay, you have the input side or the driving point side, and then you have the output side. Okay, right, and then the transfer function from output to input. Okay, transfer function V2 is the output, V1 is the input. We describe this 2-port network by this transfer function. Okay. Okay, so now we have a transfer function in the Laplace domain, and how do we convert the Laplace domain to the frequency domain? Using the Fourier transform. Okay, you all heard of these terms, Laplace, Fourier, all this. Anybody has not heard of this term before? Okay. Okay, so basically you convert from the S domain Laplace to the J omega domain, which is Fourier. Okay, so this is how we get the frequency response from the Laplace transform. We substitute S by J omega. Okay, omega is the frequency information. Okay, all right. Right, so remember, previous slide, we got a transfer function in terms of S. Now we substitute S for j omega, and then we will have V2, V1, j omega. Which means that we have after we simplify, you get a numerator on top, denominator at the bottom. Okay, and this will be a complex number. Okay, real, imaginary part, right? And then complex number, of course, we can change it to a different format, which is the magnitude and phase. Okay, this part, people understand what's going on here? Okay, this is a lot of mathematics, all right? Okay? So just to give you all a quick appreciation, right? Why do engineers need to learn about mathematics, need to learn about complex numbers? Right? Anybody? Any idea? Why do we need to learn about complex numbers? Okay, of course we need to learn about so that we can analyze filter lah. Okay, all right. But the complex number, if you think about it, is a very useful number, right? Why is it useful? Because in one number, it has two pieces of information, right? The real part and the imaginary part. So these are two different information type in one number. Okay? In the real number, it's only one information, right? X equals 1, X equals 2.5, X equals 3. Only one information is there. Whereas for a complex number, you have two different information, right? The real part and the imaginary part. Okay? Which can also be mapped into a different format, which is the magnitude and the phase. Okay? So now if I give you a sine wave, or give you two sine wave, how do we describe the sine wave? Magnitude, right? Which is the amplitude, right? That's the magnitude. And then the phase of the sine wave. Okay, right? So one sine wave is like this, another sine wave is slightly delayed. Right? It means the same magnitude, but the phase is different. Okay, one is sine omega t, one is sine omega t plus 45 degrees, plus 30 degrees. Okay? So the complex number is very useful mathematically, not just for filters, right? Any sort of analysis and processing where you have two different elements, okay, you want to combine together, right? The complex number is very useful, okay? It's like a vector lah, okay? Okay, so you can see, right, transfer function, you end up with a magnitude and an angle of phase, right? Okay? And then this is the different mathematics of what the magnitude is. Magnitude, you can write it in terms of a square of the real part and the imaginary part. Okay? Alright? So basically is that you have a vector, real imaginary. The magnitude actually is the length of the vector. Okay? And then the phase you can write also, right? The phase is the inverse arctangent or inverse tangent, right, of the imaginary with the real. Okay? So you have a real part, imaginary part. This is the vector. So this length is the magnitude, and the phase is this angle here. Okay? Okay, how do we specify a filter? All right? How do we specify a filter? All right? So you see, we specify, so for example, this is a low pass filter. All right? So we will specify what is the pass band, okay? What is the stop band? And then what is the maximum attenuation in the pass band, okay, by this number? And then what is the minimum attenuation in the stop band, which is this number? Okay? Right, so these are all the different parameters to specify the filter. Okay? And then, and you can map it, this was for low pass, you can map it to a high pass, a band pass, stop band, okay? Band stop filter. All similar. Okay? And then of course the question you ask is, what about how steep this filter is? That means the transition from pass band to stop band. Okay? you cannot have a vertical transition point. Okay, because you'll find that in order to have a vertical transition from pass band and stop band, your filter will be very, very high order, very complicated. Okay, all right. Okay, so there will be a transition. So this is a transition band. Okay, all right. And typically, for example, for the attenuation, we will specify like this. Okay, attenuation is minus 20 log magnitude of the transfer function. Okay, so why minus? Well, because this number at the stop band will be a negative number. All right, and then we say attenuation. The word attenuation already means I'm suppressing. So this is just English. Okay, right? So attenuation is like the negative gain. Okay, all right. So 20 log gives you the attenuation in terms of dB. dB. Okay. Okay. So here we talk about this concept called a group delay. Group delay. So what is group delay? Okay. Group delay basically is if a signal goes through your filter, all right, and if your filter just delayed in the time domain, delay by 1 microsecond, delay by 2 microseconds. Okay. This delay, all right, we call it the group delay, D. Okay. And then you can see, right? So if V1 is a summation of sine waves, all right, then the output, okay, if this filter has just a group delay of D, it looks like it's a phase shift, all right, okay? And, sorry, it looks like a time shift, okay? Time shift means that the phase delay is linear, okay? The phase linear translates into a constant delay in the time in the group delay. Okay. So why is this group delay important? Right. So a circuit which has group delay or which has linear phase means that if I have different kind of pulses going through my system, right, they will be equally delayed. Okay. All parts of my signal will be equally delayed. Okay. So my signal pulse will not get distorted, right? That means for different frequency, the time shift is the same, right? So you can imagine, right? If I have a circuit in which the time shift is different for different frequency, then if a certain shape go through my filter, it will be distorted at output because this shape will have different frequency component, right? And if the delay is different for different frequency component, then my output will not be the same as my input. The shape will be different. Okay? Okay, so basically you can see these are the different cases lah. Okay? No group delay is just go straight. Constant group delay means everything is shifted. And then if you have a non-constant group delay, you end up with distortion. Your signal shape is distorted. Okay? So why is this important? Well, in a lot of circuits, you are trying to transmit 1 and 0. Okay? 1 and 0. Right? Through a cable or something. Alright? And what is 1 and 0? 1 is different pulses law. Right? High is a 1, low is low is 0. Alright? So if you want to transmit 1, 0, 1, 0 is high, low, high, low, high, low. It's like a different pulse. Okay? And then if it goes through your circuit at the other side, you want to recover, right? What is 1010, right? So you need to recover. So if your circuit somehow has got non-constant group delay, you may have problem recovering the signal. You can't tell, okay, is this a 1 or 0, okay? Okay, so here we talk about instead of the Laplace domain, we talk about the time domain. Okay, time domain, right? So if you think about, let's say at the input, right? If I put in a unit step, U of t is a unit step, okay? 0, and then it goes up to 1, a unit step. All right? If I put it through my filter, what does the output look like? Okay? All right? So, you will see that output, of course, this is a real filter, so it cannot be instantaneously from 0 to 1. Okay? There will be some transition, okay, and then slowly it will settle to the final value. Okay? Right? Yeah, so we are assuming here, okay, we are assuming this is a low pass filter lah. This is low pass filter, right? Low pass filter. So we know for low pass filter, it will pass what? Low frequency, including DC, right? So DC is 0 frequency, right? Okay? So unit step over here is value is 0, right? So here all will be 0, right? Unit step time, when the time is very big, far away, is DC of 1. So here, far away, DC also of 1. Okay? The problem is here in the transition. Okay, in this transition point here, what is the frequency? What is the frequency? When it goes from 0 to 1? What's the frequency? Huh? Very high, right? Very high, right? This is a vertical edge, very high frequency, you know. Okay? That's why your filter got problem. Your filter is a low pass filter, right? What happened to all the high frequency part? Got filtered out. So the filter cannot pass the vertical edge. That's why the filter can only slowly go up. Okay? Alright? Okay, so basically, any sharp edge, that means got high frequency component. That's the simplest way to understand. Okay? Okay, so these are the different parameters we use to describe this filter time domain response, right? You have the delay time, right? Which is typically measured from how long it takes to get to 50% of your final value. Okay? You have the rise time, okay? Which is the time taken to get from 10% to 90%. Okay? That's typically the measurement of rise time. Okay? Then what is the final value of the output? Okay? And then here, sometimes there's also an overshoot. Okay? Okay, what's the percentage of overshoot ratio? Okay? All these things. Okay, so now we come to something useful now, okay? So before we talk about op-amp based filters, we need to talk about op-amp based amplifier. Okay? Op-amp based amplifier. Okay, so what is the purpose of an amplifier? To amplify something lah. Okay? Alright, basically it's to give it some gain. Alright? Okay? Okay, you all know this is the op-amp, right? Op-amp, right? Operation amplifier, right? So you may ask, you already have an operation amplifier. Operation amplifier already got gain, right? Then why do you need a op-amp based amplifier? Correct? Your operation amplifier already got gain, right? Right? Then why do we need to talk about op-amp based amplifier? Just use the op-amp lah. Is that a good idea? Is that a good idea? Huh? Come, decide. Is that a good idea? Just use the op-amp lah. Why must use the op-amp based amplifier? Low input impedance, what? Gain too low. Not true, no? Some op-amp is 100 dB, 120 dB. That means gain 100,000, gain 200,000, you know. And also not low input impedance. Some op-amp very high input impedance. Sorry? Mismatch problem. Mismatch of what? Okay, so mismatch give offset lah. Offset lah. Offset. Okay, offset. Right? Actually, the reason is quite simple. Alright? And the reason that people already found this historically when they first designed the first op-amp. So it's true, the op-amp gain can be very high. 10,000, 100,000, 500,000. But then they found there's a problem. What's the problem? It's not well controlled. It's not well controlled, right? So you manufacture 100 of this op-amp, you measure the gain one by one. One could be 100,000, one could be 200,000, one could be 50,000, right? So the gain is not well controlled. That means the variation, okay? Right? So obviously it's hard to use, right? Right? It's hard to use, okay? Not only the gain is changing, the gain changes with temperature also, you know? Right? So that's why. But how can we use it? So we have to use the op-amp. We need to stabilize the thing, right? And how do we stabilize it? We use the important concept of feedback, right? We use feedback. Okay, that's where feedback comes in. Okay, so that was the other great invention. Okay, feedback. Okay, right? So that's why we come up with a op-amp based amplifier. That means we use the op-amp, but we use it inside a negative feedback loop. Okay? So here is your op-amp. Okay, two input, transfer function or gain function in Laplace domain, one output. Okay, so this is a simple open loop. Okay, transfer function of the op-amp. This is the magnitude of the gain A. Yeah? You can see it's like this, very high gain at low frequency, and then beyond a certain pole frequency, it drop off. Okay, drop off. The gain drop off. Okay. So basically, we say this is like a single pole response. Okay, this op-amp got a single pole, right? Okay. We call this the point here 3 dB. That's when the gain dropped by 3 dB. Okay. So here we approximate by a straight line and a straight line coming down. Okay. The actual thing will be a slightly roll off lah. Okay, and at that point, there's a 3 dB drop from the low frequency. Okay, that's why it's called a 3 dB bandwidth. Okay, when the gain dropped to 1, we call it the unity gain bandwidth. Okay, right, and A0 is a low frequency or DC gain. Okay, so this is the simple transfer function of such an op-amp. Okay, a single pole response op-amp. DC gain A0, pole frequency omega p. Okay, this is the transfer function. Okay, this is a simple body plot. You all heard of body plot, right? You heard of body plot, right? Body diagram. You must know, You must know, okay? All right. Okay. So with this building block, we can build what we call an inverting amplifier. Inverting means the output is the inverted version of the input. Okay? Right? And what is the transfer function of the inverting amplifier? V over V in is what is the transfer function? Okay, so the simplest way to analyze this is first you just analyze it and assume the op-amp is ideal first. Right? Okay? Alright, remember you all did analysis, right? Second analysis. First order analysis, you assume the op-amp is ideal. Right? Ideal meaning what? What's the op-amp gain? Infinity, right? Very high. Okay? No mismatch, no offset, nothing. Okay? Okay? That means very high infinite gain, right? No offset. Which means that this point and this point is the same. What we call the virtual ground. Okay? Right? Because this voltage is, okay, this is where we need to do some understanding, right? Why do we come to this result? Because we say this output is a finite voltage. Right? This output is a finite voltage. Okay? And if the op-amp gain is infinite, it means that there must be zero voltage across the input. Right? That's why we say this is like a virtual ground. That means this voltage is equal to this voltage, right? That means this now is ground. This current is VI divided by R1, and this current got nowhere to go, but it will go through here, and then we can work out what is the output. So output is ground minus, because current is flowing this way, IR2, and I is VI divided by R1. So the transfer function magnitude is R2 divided by R1. Okay? That's the ideal. That's for the ideal op-amp. But now if you put the real op-amp inside, which has got finite gain, okay, this is where you work it out. Okay? Right? You can work out and you find that this is the frequency response. Okay? So important question. If I give you this circuit, how are you going to analyze it? How are you going to analyze it? You analyze this way, okay? So now, with the real circuit, this point is not ground anymore. Okay? It's not ground anymore. What is this point? What's the voltage at this point? Huh? No, it's not zero. Zero is zero if you assume it's an ideal op-amp with infinite gain. Okay? Yeah, virtual short is you assume it's ideal op-amp with infinite gain. Okay? But now you have a real op-amp with a real gain. Okay? But we still apply the same equation now. Okay? 0 minus this voltage, which we will call V, don't know what we call it, V minus or whatever, right? 0 minus V minus is the voltage across the input of the op-amp, multiplied by the gain is equal to the output . Okay, so that's how you analyze it. For op-amp with a real gain, this is how you analyze it, okay? Right? Okay? So you don't believe me, you go back, you analyze the circuit this way. You get the same result. Okay? So you just analyze it. You just put this voltage is output divided by A . Okay? Alright? So you just put divided by A in the first place. Then later on you replace A by this equation. Okay? You will come up with this frequency response. Okay? So those of you who are not very familiar, please go back and work it out. Okay? Very important. Because a lot of other circuit, we are relying on this analysis. Okay? Right? So if you do that, you find that this inverting amplifier has this transfer function. Okay? DC has a gain of R2 over R1. It has a 3 dB frequency, okay, omega P inverting, and this is the value of the inverting amplifier, of the inverting amplifier frequency, 3 dB frequency, and then it will drop off. Okay? Alright? And we can do the same thing for the non-inverting amplifier. Okay? So here you see is a non-inverting amplifier. Why is non-inverting? I apply the input to one side. Okay? Ideal op-amp, it will also appear here. Right? Virtual ground. Right? Therefore the current is VI divided by R1, and the output is VI plus current times R2. Okay? Okay, you all should know how to analyze it this way. Okay? That is for the ideal op-amp. For the non-ideal op-amp, you do the same thing, right? This voltage VI minus this voltage, and this voltage is V out divided by A. Okay? And then you just analyze it in the same way. Okay? Right? So interestingly, if you compare the two type amplifier, inverting and non-inverting, right? First one we analyzed was inverting. This is non-inverting. So if you compare, you find that they look like this. This one is the op-amp open loop, okay? Op-amp open loop frequency response. What is this? Okay, the non-inverting is the red curve, and the inverting is the blue curve. All right. So there's a slight difference between the transfer function of the inverting versus a non-inverting amplifier. Okay. Okay, you all know where this transfer function come from? Output divided input is A divided by 1 plus A beta. Do you all know where this expression comes from? From feedback theory, From feedback theory. Okay? So feedback theory is that A is the forward gain, and then the output, I will negative feedback back to the input, okay, subtract from the input with a feedback network called beta. Okay? And then if you analyze it, the transfer function is A divided by 1 plus A beta. Okay? Right? And in this equation, you can see here also, right? The power of feedback in stabilizing op-amp with changing gain. Okay? So now you look at this equation, basically is that if my A is very big, okay, but it's not well controlled, okay, this transfer function, as long as A is very big, this whole thing is approximately 1 over beta. Okay? Right? Very simple, right? If A is very big, then A beta is much bigger than 1. And therefore A divided by A over beta is 1 over beta. So as long as your feedback circuit gain is well controlled, right, that will control the gain of your overall amplifier. Okay? Right? Okay, so now we talk quickly about first order filter. Okay? Remember last lecture we talked about first order noise shaper? Now first order filter. Okay? We will talk about bilinear type filter, how to realize it, do some scaling, or how can we implement a first order filter using active RC, okay, and what are some design procedure and guidelines. Okay. Okay, so first, what is a bilinear transfer function? Right? As the name implies, very simple, right? Your transfer function has got numerator, denominator, and both of them are first order. Right? That means S to the power 1. Okay, the maximum power S is 1. Okay? So numerator is B1S plus B0, and the numerator and the denominator is A1S plus A0. Okay? And then you can simplify this to a numerator which has 1 0, and the denominator is 1 pole. Okay? Right? So bilinear filter means first order filter, maximum 1 pole and maximum 1 0. Okay? Sorry, 1 pole? 1 pole 2 0? 1 pole no 0. Yeah. It's still bilinear. Yeah, we mean that the pole is at infinity lah. Right? So you can consider like there's 1 pole, the pole is very far away. Okay? Or you can have No, you can have 2 0. Once you have 2 0 2 pole, it's not bilinear anymore. No, 2 0, that means it's not bilinear. Okay? Okay, you can have only 1 0, no pole, but the pole is very far away. Or you can have 1 pole and no 0, which the 0 is also very far away. No pole, no zero. Then okay. Then it's zero. Basically DC. It's DC. Okay? Okay. So this is what? Simple example, right? 1, 0, 1 pole, right? Right? The 0 is at -5, right? And the pole is at -2. Okay? So you plot it on the S domain plane, real, imaginary, 1 pole at -2, 1, 0 at -5. Okay? Okay. So what does the frequency response of this kind of a bilinear transfer function look like? Okay, so from the Bode diagram, you know, right? Bode diagram, right? What is the magnitude response due to the 0? Go up, right? It goes up, right? Right? Goes up, the pole opposite direction go down. Okay? So now, depending on where is the location of the pole and what's the location of the 0, you have different kind of response. Correct? Okay? So you see the 0 is going up, the pole is coming down. Okay? So if the 0 is less than the pole, what happens? It will go up first, and then it will flatten out. Right? Whereas if the pole is less than the 0, what happens? It will go down first, and then flatten out. So the location of the 0 and pole will change your overall response. Okay? If the pole and 0 are exactly the same, flat, okay? They'll cancel and you get DC lah. Okay? 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 And then here is the similarly for the phase. The phase, you know that the 0 means what? The phase will increase, right? Increase, right? At the 0 point, it will be a 45 degrees phase gain, right? And then finally, it will be a 90 degree phase gain at high frequencies. And then for the pole, it will be opposite, right? Exactly at the pole, you have minus 45 degrees phase lag, phase drop, right? And then very far away, it will be a minus 90 degrees. Okay? Yeah. No. 2 is the 0. 2 is the 0. 2 is the 0. Oh, no, sorry. The 2 is the pole, yeah, 2 is the pole. Yeah, the 2 is the pole. No, he's plotting this like this, and then when you subtract, it will come down. Yeah. Yeah. So you see here is subtract. But now when it's plotting like this. You see? Okay, it's a bit confusing. That means he's plotting this one is a 5, right? Right? So 5, you go up. Right? He's plotting this is as 2, no negative. That's why you go up. You see? And then you subtract. Overall, you'll come down. Okay? Okay, so basically you see here is the magnitude response, alright? Okay? And then these are all the straight line Bode plot approximation. Okay? That means the sharp corner, 0 go up, sharp corner, pole come down. Okay? These are all the straight line Bode plot approximation. But when you do the actual simulation and calculation, right? Of course, there's a gentle roll off. Okay? So these are the 3 dB points, 3 dB, 3 dB. Okay? Here is the straight line Bode plot approximation of the phase. But if you do the real simulation, you find it's a gentle. Okay? It's no sharp edges here. Okay? Alright? Okay? So this is, you can generate this from MATLAB. MATLAB. Okay. So you know how to, if you need to do this by hand, you know what to do, right? That means you calculate the magnitude for different frequency. You know? Alright? For different frequency, you calculate what's the exact magnitude and then you plot it. Okay? Same thing for the phase. Right? Of course, the tool will do it for you automatically, right? You calculate, right? So that so that's why it's low pass. Here is very flat. Then when it come to the first turning point, right, you slowly drop down. Okay? Okay? 3 dB is somewhere here. Here. See, here is 0.246. Right? So this is the initial, this is the bilinear transfer function gain at DC. Okay? So at DC, what is this gain? What is this gain at DC? This transfer function? Sorry? No, just look at this. Look, this transfer function. What is the value of the transfer function at DC? S equals 0. DC 2.5 lah. 2.5. Okay, 2.5. So this will be 2.5 in dB. In dB. That means I expect 20 log 2.5 to be equal to 8 dB. Okay? Right? So the magnitude, if I want in dB, I have to take 20 log. Okay? Right? No, so why you want to plot in dB? Because the body plot, although straight line, right, is based on dB scale. Okay? Right? Okay? And then here is that you can calculate what is the group delay using this formula. Okay? That means you take the phase of the transfer function, take the derivative, okay, d phase by d omega, right? You will get the expression for the group delay, okay, d in terms of omega, right? And then you plot it, you find that this is the group delay. Okay, so at very high frequency, the group delay is roughly flat, okay? But from DC onwards, there's a sharp transition. So the group delay is not constant for this bilinear transfer function. Okay? Okay. So basically, now we know, right, is for any bilinear transfer function, depending on where we put the zero, where we put the phase, where we put the zero, where we put the pole, you have different kind of frequency response. Right? So you put the zero first and then the pole later, you have a little bit of a high pass, right? You'll go up and then you will saturate. So this looks like a simple high pass filter. Okay? That means you will pass higher frequency, right? And you will attenuate the lower frequency. If I put the pole first and then the zero, what happens? I will drop first, right? Because of the pole, I'll drop first and then I will straighten out at high frequency. Right? That means I will pass more low frequency compared to the high frequency. Okay? Alright? Okay, so you can see here different kind of response. Okay, here is where you can see for example, this one, there's a zero at very high frequency. Okay? So it looks like you only have one pole here. Okay? Right? And then if you have different sign of the pole and zero, you have a different type of frequency response. Okay? So you see, even for a simple bilinear transfer function, right, you can have a lot of different combination to give you different kind of frequency response. Okay. Okay. So how do we map the bilinear transfer function into a real circuit? Okay, into a real circuit. Okay. We can do this if we just use simple passive elements, right? That means capacitor and resistors. Okay, anybody know why we don't use inductor? In this slide, why we don't use inductor? Sorry? Equal to what? 0 point. Why inductor equals 0 point? Okay, I think in theory you can, right? But in implementation we don't do because historical, is because it's very difficult for us to implement an inductor in a IC, in a chip. Okay, right? It's very difficult to implement. Right, that's why you see in the IC chip, we implement resistor, we can implement capacitor quite easily. Okay, but it's difficult to implement an inductor. Okay, that's a simple reason now. Okay. What's the reason? Is it? Anybody know why inductor is difficult to implement in a chip? Okay, because you think, I mean, what actually makes up an inductor? Wire, right? No, it's a core, right? It's a core, right? So the inductor is a core, and what does the core mean? It means that there's what's the energy? It's magnetic energy, you know, right? So in the inductor, the energy is stored in the magnetic field, right? That's why you have a core. Right, the core is to build up the magnetic field inside the core. Okay, so you can see the problem straight away, right? The IC technology is 2D or 3D. It's a lot of 2D. It's a planar, right? Right. So you cannot build a 3D core, not possible. Okay, but you can build a 2D core, you can build a 2D core. Okay. But the 2D core is not a very good inductor. Yeah. What? The value, of course, is small, but also the efficiency or the what's the term they use? The N factor or something. It's not a very, the energy storage is not very good because you don't have 3D, right? You need a 2D. Okay. But for the RF people, that's what they do, They try to build big inductor, okay? But the efficiency is not very high. So you cannot build very high efficiency inductor, right? Okay, that's the basic reason. Up to today, right? People cannot build high quality inductor using IC technology, okay? Because fundamentally your IC is a 2D. It's a 2D. Okay. Although the latest transistor is not really 2D the FinFET actually is coming up. Okay. Okay. So now basically if we implement a circuit using passive element, we can get a bilinear transfer function with 1 0 and 1 pole, right? So for example, such a circuit, right? Input here, we take the output here. This is the transfer function. Okay, so you have 1 0, you have 1 pole. Okay, right? In this case, the 0 and pole same magnitude, right? Okay. Okay. Okay, so let's do a quick example, right? Example. Okay, of a low pass filter, right? So say you want to design a first order passive low pass filter to meet these requirements. Okay? That means I want the minus 3 dB at 1 kilohertz. I want my stop band to be at least minus 30 dB down. And I want my phase shift to be less than 75 degrees. Okay? So, can I implement using a low pass filter? Okay, so we see here, right? Low pass means I have 0 dB. So passive element means that there's no possibility of gain. Okay? Because I'm using all passive element, I cannot have a gain greater than my input. Okay? This is simple physics lah. Huh? If I use passive, there's no energy source, you cannot increase the gain. Okay? Right? So at low frequency, my gain is 1 or 0 dB. Okay? And then I want 3 dB at 1 kilohertz, so I know that this edge has to be at 1 kilohertz. Okay? Right? And then it's a bilinear, right? That means I'll hit a pole, that means my pole must be at 1 kilohertz. Okay? And then it will start dropping, alright? It will start dropping. And then I want the attenuation to be at least 30 dB. Which means that I need the 0 to be at least here. Right? It must have dropped 30 dB down. Okay? Alright? So with this, I have all the information I need for my bilinear transfer function, right? What's the DC gain? What is the pole frequency? And what is the 0 frequency? Okay? Right? So we can write out. Alright? So if you implement the bilinear using R1, R2, and C, okay, you can analyze it. You can know what is the zero frequency term and what is the pole frequency term, and then you just solve it using all these constraints. Okay, the 0 must be at 1 kilohertz, right? And then because this is a simple bilinear, this slope is also fixed to be what? Minus 20 dB per decade, right? Coming down. Okay. The body plot, the body plot approximation, right? Right? So this slope is coming down at minus 20 dB per decade, and we want to have the 0 when it hits minus 30 dB. Okay? Right? See, the other way to write it is this lah. You write your transfer function, and because you know this is flat, it means the high frequency gain is minus 30 dB. Okay? Alright? So high frequency, what's the value of S? S equals to infinity lah, right? You can make S equals to infinity. So DC, you make S equals 0. Very high frequency, you make S equals to infinity. Okay, these are the rough ways to do a calculation. Huh? Okay. So here you get from the pole at 1 kilohertz, you have this equation. All right. And then for the minus 30 dB, all right, attenuation, you can calculate how many decades from the pole to the 0. Because you know it's 20 dB per decade. So if I need 30 dB, how many decade? How many decade is it? Okay? So decade, you need to translate in 10 to the power, okay? Okay? So that means that roughly 0.03, right? That means the pole divided by the 0 is 0.03. Then you can calculate what is the 0 frequency, okay? All right? And then we can check what is the maximum phase shift. The phase shift, all right? So we calculate, knowing what's the 0, knowing what's the pole, take the arctangent, you find that the phase shift is roughly 67.5 degrees, which is less than the required 75 degrees. Okay? All right? Okay, so that was, so once we know all this, all right, we have to choose the different component values, right? Where is it? Yeah, because now to implement this value function, we have three components that we use, right? We use two resistor and one capacitor, right? So what should be the value of this capacitor and resistor? Okay, so you have two data point, right? Where's the zero? Where's the pole? These are only two equation. Okay, but you have three unknown. So how do we solve this type of equation? Three unknown, two equation. You can pick one value lah. You see, right? So that's why I say here, you go and pick one value first. Yeah, let's say you pick the capacitor 1 microfarad first. You see, then you solve for the other two. Because you got, that means once you pick the capacitor, you got two unknown, two equation. Can solve, right? Right? Okay? Alright? And then you can check, you can double check. Once you put all it in, you can double check what's the attenuation. Okay? So if you use MATLAB or use Spice to simulate, you see that it looks like this, right? Pole 0. Then here is your phase shift. Okay? So the phase shift at 0, at low frequency DC is 0 degrees. At high frequency is also 0. Why? Because the phase shift or the 0 and the pole just cancel one another. Right? 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 Because first you hit the pole. So the pole will want to give you a minus 90 degree phase shift, right? When everything is stabilized. Then you hit the 0. The 0 want to give you a plus 90 degrees at very high frequency. So they'll cancel one another. Okay, that's why you see the phase shift, right? 0 at the beginning, DC, 0 at very high frequency. In between, there's some disturbance because you hit the pole first and then you hit the 0 later. Okay? Okay. Let me just see. How many more slides first? Okay, maybe we take a break now. We take a 15-minute break before we go to the next topic on normalization and scaling. Okay? Any questions first before you go for a break? Okay, basically very important for this bilinear and for all this filter thing, right? Please make sure you understand all this transfer function in the Laplace domain. Okay, how to manipulate all this thing, how to get what's the DC gain and DC phase, put S equals 0 or omega equals 0, right? At high frequency, how to find out, okay, S equals infinity or omega equals infinity. Right? So you see we are moving between Laplace domain and frequency domain. Okay? So if you just want to know what is the DC, you don't have to go to the frequency domain. Just go to the Laplace domain. Just put S equals 0. Very simple. Alright? Very high frequency, you can also just stick to the Laplace domain and just put S equals infinity. Okay? And see what's the approximation result in the transfer function. Alright? If you want to know anything in between, 1 kilohertz, 5 kilohertz, all this, you have to go from the Laplace domain to the j omega Fourier domain. Okay? And then calculate what's the magnitude, what's the phase. Alright? Okay? So, and then you need to know the body plot. What's the approximation? Straight line at the pole come down, straight line at the 0 go up. These are all the body approximation, straight line approximation. Okay? Okay, let's go for our 15-minute break and then we can come back. Okay? If there are no questions. Okay, I'm still here. If you have any question, you can ask me also. Okay, because we've got a lot of slides today, try to restart now. Hopefully, I want to roughly show you the homework question also. All right. Okay. Anybody still outside? Anybody still outside? Okay. Okay. So now we come to this this concept called in filter design called normalization and scaling. Okay? Why is this being used? Okay, so actually the reason is very simple, right? in the early days of designing all these analog filters, because you can design different, you can design a filter with different frequency points. Okay, for example, low pass, right? You can design the minus 3 dB to be 1 kilohertz, to be 100 kilohertz, to be 1 megahertz, all right, 10 megahertz. Okay, so in the early days when they design using table, using a table. That means you pick these values, all right? You can design your low pass, all right? And to handle all these different cases, they use this concept called normalization. That means I give the table allows you to design a low pass filter with a cutoff frequency at a normalized frequency of, let's say, 1 kilohertz. Okay? Once you have this, and you can then denormalize, right, to get different cutoff frequency. Whether you want 1 kilohertz, 100 kilohertz, 200 kilohertz, you can just denormalize the thing. Okay? So this will make the design table simple. Okay? Otherwise, you have infinite number of design table, right? You want 1 kilohertz, you want 2 kilohertz, you want 3 kilohertz, wow, right? So that's why they have this normalization concept. Okay? And also allows you to avoid dealing with very large or small parameter values. Okay? Okay? And then to get your actual implementation, you will do a denormalization to scale the parameters, all right, depending on what you want. Okay? Okay, so in the filter design, we always design using normalized parameters, and then we do the scaling later. Okay? So this is the concept, okay? Okay, so in terms of real mathematics, what does it mean? Okay? That means I have a normalized frequency which I call omega n. Okay? Alright? And Kf is the scaling factor. Alright? That means I will design everything using omega n, and then finally I will apply the right scaling factor to shift it to the frequency I want. Okay? Okay? So when you move from omega to omega n, it's called normalization, because n means normalized. Right? And we move from the normalized omega n to the real omega, we call it denormalization or scaling. Okay? Later on when we look at the example, it will become clearer. Okay? What's the important thing? The important thing is that the impedance will start changing. Okay? Because when you change the frequency, you will change the impedance. Okay? Why is this? Because for the capacitor, right, it's a frequency dependent impedance. All right? What's the impedance of a capacitor? 1 over j omega c, right? So if I change the omega, the impedance Z of C is changing. Okay? All right? Okay, so for example, if I have an inductance, impedance is omega L, right? The impedance of an inductor, all right? Omega L. And then now, if I express the omega in terms of normalized, it becomes Kf omega NL, right? That means I can treat this as a normalized parameters, omega n and Ln. Okay? Where Ln equals to the frequency scaled version of L. Okay? Okay? And then that's normalization. You denormalize, just do the inverse. Okay? The factor is Kf. Okay? Kf is the frequency scaling factor. Same thing for capacitance. 1 over omega C. Transform. Omega is omega Kf omega NC. Become a normalized capacitance value. Okay? Which is related to the real capacitance value by Kf again. Okay? Of course, for resistor, no change. Okay? Resistor, no change. Because why? Resistor is not frequency dependent. Okay? Okay. All right. So that was frequency scaling. So now we can say what is magnitude scaling. Okay? Magnitude scaling. All right? Magnitude scaling for frequency remaining unchanged. Okay? So we want to keep the frequency the same. We just want to change the magnitude. Okay? So this is impedance Z is equal to the magnitude scaling factor Km times the normalized impedance Zn. Okay? So here is once again inductance ZL equals omega L, and we transform it to a magnitude scale Z of Ln. Okay? Okay? So we can do it for inductance, we can do it for capacitance. Now, because we are scaling magnitude, we can also scale it for resistance. Okay? Okay, so why do we want to do all this? Okay, what's the purpose of all this? It's because when you try to implement an actual filter, you need to use real values of resistor, capacitor, okay? Inductor, if you build this thing on a board, PCB, right, you can put an inductor there, okay? On a chip, of course, inductor is more difficult, okay? But what are the values that you can use when you want to actually build this kind of filter? Okay? Certain values are easier than other values. Okay? So, if for example you want to build a filter on a chip using resistor and capacitor, there are certain constraints on how big the resistor can be and how big the capacitor can be. Okay, that's why you need to do some scaling here. Okay? So on a chip, you cannot say I want to build a capacitor of 1 microfarad. Okay, it's just not possible. Because why? Because it'll be huge. You know, yeah, the area to build this capacitor will be huge. Okay, impossible. All right. So on the chip, maybe you can use capacitor of maybe a 10 picofarad, maybe 20 picofarad or 50 picofarad maximum. You can't even build a 1 nanofarad capacitor on the chip, right? Because it'll be huge. Okay. Same thing for a resistor. Okay. Okay. You cannot build a 1 gigaohm resistor on a chip, right? Because it's huge. The resistor will be very big. Okay. Which means that when we implement, we can only use certain values. All right. Whether on the chip or even on the board. All right. There are a few component values which are very common. Right, on the board, maybe 1 microfarad is a very common capacitor. If you go to the lab, you just go to the lab, and you ask the lab guy, right? Okay, what capacitor you have? He'll tell you 1 microfarad, 0.1 microfarad, maybe 10 microfarad. Okay? Okay, so because of that, we will have to do all this scaling to get the component values to the values which we can implement. Okay? All right? So sometimes you can also combine the frequency and magnitude scaling. Okay? Alright, so basically the summary is this. When we design a filter, we will start the design using normalized values. Omega n, Ln, Cn, Rn. Okay? And then after that, after we finish the design, using a normalized value, we will then scale it to the actual values that we need or we can use. Okay? That is the simple concept, right? And we'll see this later, right, in one of the examples. Okay, so scaling. So we go back to the previous example, which was a bilinear function. All right, remember we had one of the 0 and pole at 1 kilohertz, right, and another one low pass. So I don't know. It was some bigger number than 1 kilohertz. Okay, all right. So here, what we do is the first thing, we go from this bilinear transfer function in the S domain, we normalize it, and this to become the normalized domain, S over N. Okay, right? So this is the normalized version. Okay, And then from the normalized version, all right, we can get the normalized parameter values. Okay? R2 normalized, R1 normalized. Okay? And then we calculate what is the component values again after normalization. All right, this is what we get. Okay? So here you can see that resistor 1 normalized is how much? 969,000. Almost 970,000 ohms or 970K. Okay, whereas the R2 normalized is about 30K ohms. Okay? Right? And then we do the frequency scaling. Okay, that means we denormalize the pole frequencies, all right, to get the capacitor values. Okay? All right? So resistance is not changing because of frequency scaling. Resistor don't change, right? But the capacitance value will change. Okay? All right? So it changed from the previous, this is 1 microfarad, right? Once you do the frequency scaling, it dropped to 0.159 nanofarad. Okay? And then we can do the magnitude scaling of C back to microfarad. Okay? Right? And then when you do the magnitude scaling, the value of resistance also changed now. Right? Magnitude. It dropped from 30K down to 4.77 ohms. Right? It dropped from 970K down to 154 ohms. Okay? Okay. So now we talk about another type of filter. Alright? So this is now a filter which we derive from the inverting amplifier that we analyzed previously. Right? Inverting amplifier, right? 2 R1, R2. Okay? Right? Inverting amplifier, right? R1, R2, right? Okay? So now if we don't use resistor and we say we are using some sort of impedance Z1, Z2. Okay? The analysis is still the same. The transfer function instead of R2, R1 becomes Z2 over Z1. Okay? And so now if you say Z2 over Z1 is equal to Y1, Y2, right? Impedance is admittance. Y is 1 over Z, okay? Then if each of these are linear, numerator, denominator, you have a simple bilinear transfer function again. Okay? Z1 and P1, right? Okay? So, how to implement? Okay? 2 different ways. 2 different circuits can do this. Right? So, if Z1 is, I put resistor in series with capacitor. Alright? So, both of them are series resistor capacitor. Or, I put them, Z1 is capacitor in parallel resistor. Okay? You can get similar kind of expression. Okay, so example, right? So in this example, we will say that Z1 is C1 in parallel with R1, Z2 is R2 in parallel with C2. Okay? If you don't believe me, you just go back and try. Okay? So what is the Laplace equation for this? C1 in parallel R1? Anybody? Okay, so when a thing is in parallel, to make things simple, we use the admittance Y, right? So in things in parallel, it means that Y1 plus Y2, right? You just add. Okay? If it's in series, we just use the impedance, right? Z1 plus Z2. Okay, so this is in parallel, so we use admittance, right? So what's the admittance of a capacitor? SC1, right? What's the admittance of a resistor? 1 over R. Okay? So Y1 is basically 1 over R1 plus SC1. Okay? And which means that Z1 is the inverse of Y1. Okay? Right? So basically we do this lah, right? So if you work in admittance, the transfer function is Y1 divided by Y2. Right? If you work in the impedance, transfer function is Z2 over Z1. Okay? So in this case, because it's in parallel, we will find what is the admittance, what is Y1, and then this Y2, and then we just take Y1 divided by Y2 is the T over S. Okay? So you plug in all these values, right? Because you know now, right? You want the 0 at 830 Hertz. You want the pole at 13 kilohertz. Okay? So what, straight away, what is the shape of this thing? You hit the 0 first, you go up. Right? Then you hit the pole, flatten out. So it's like a high pass function. Okay? Alright? Okay? So once again, okay, you go into the normalized domain, right? And you scale using the 1 kilohertz here. Okay? 1 kilohertz radian per second. Right? Then you can calculate what is the transfer function in the normalized domain using Y1, Y2. Okay? This will give you the capacitor value C1n, C2n. 1 over R1 we call G1, G1 normalized, G1, G2, right? And then because we know that the K factor, right, is 14.21, that means we can work out all these things, okay? And then once again, we have four unknown, all right? R1, R2, C1, C2, right? And we only have, I think, 3 equations, so we can pick one value, okay? So we pick C1n to be 50 nanofarad, okay? And then we can work out all the rest, all right? Okay? And once we have all these values in the normalized form, okay, C, N, Rn, and then we just denormalize the frequency, and then we can also scale the magnitude. Okay? Right? So once we do that, okay, we get all these values. Okay? Here we just don't scale the C lah. Okay? We keep the C at 50 nanofarad. Okay? Okay. So now we come to 2 special cases of this kind of circuit. So remember the circuit? This is the general circuit we're talking about. Okay, Z1, Z2. Okay? Inverting amplifier, Z1, Z2. Okay? So these are the 2 special cases. If Z1 is just a resistor, and Z2 is just a capacitor. Okay? Special case, right? That means R2 equals infinity, right? R2 is here. It's supposed to be in parallel C2. R2 equals infinity, so R2 disappear. Right? And then here is R1, C1, but C1 equals 0, so it goes to disappear. So the circuit simplified to a simple circuit. R1, C2. Okay? And what is the transfer function of this simple circuit? Is 1 over SCR. Okay, which actually is the integrator lah. Okay, is integrator. Right? Anything which is 1 over S times something is the integrator. Okay? Integrator means what? Okay, it's a integration function, which means that it keep integrating. Right? So, very simple, right? Look at this. What does this circuit do? Okay, let's assume op-amp ideal. Here is virtual ground. There will be a current here, V divided by R1. This current will go into this capacitor. What will happen to the voltage on the capacitor? It will just keep increasing or decreasing. Right? Right? I equals C dV dt. Right? For capacitor, I equals C dV dt. If I is constant, That means dV dt is constant, which means V is increasing, right? Okay, all right, that's why it's called integrator. Okay, here is the reverse case, all right? Input is C, feedback is R. You end up with a differentiator, okay, differentiator, okay? So something times S is always a differentiator, okay? So you look at the frequency response. Integrator frequency response is coming down. It's coming down, right? Because it's 1 over S, right? So as frequency becomes bigger, S becomes bigger, it's dropping. Okay? Differentiator is opposite, right? It's times S. That means as frequency becomes bigger, the magnitude is becoming bigger. Okay? Okay, so now we want to think about what happens if the op-amp you use is non-ideal. Okay, it's non-ideal, right? So we go back to the assumptions about the ideal op-amp, right, and how it helps us in our analysis, right? So remember, what is one of the property of the ideal op-amp? We say infinite input impedance. Okay, no current is going in. Okay, if you, for a real op-amp, if you use the MOS, okay, you're looking input looking into a gate. Okay, it is quite true. Impedance very high. Okay, it's high. Okay. The other assumption for ideal op-amp is what? Output resistance or output impedance is 0. Right? For the ideal op-amp, the output impedance, output resistance, looking at the output, looking from output looking in, right, is 0. Okay? Right? This also is quite valid. Okay? When you do feedback actually lowers whatever is the real output resistance. Okay? Third assumption of the ideal op-amp is infinite gain. Gain is infinity. That's why you got virtual ground, right? Okay, this is not true. Any real op-amp that you build and design will have a finite gain. Okay? So, in part 1, when you learn about designing op-amp and all this, you'll find that, yeah, you can design op-amps. If you use MOS transistor to build an op-amp, you can have a gain of, 60 dB, 80 dB, 100 dB, depending on how much current you're willing to spend. Right? Okay, but the gain is finite. Okay? Alright? Okay, then the other assumption for the ideal op-amp is that the bandwidth of the op-amp, the minus 3 dB bandwidth, is infinite. Okay? Any frequency go into op-amp can go out. Okay? Alright? That is the ideal op-amp. But we know that for a real op-amp, of course, the bandwidth cannot be infinite. That means the minus 3 dB point, the pole, alright, cannot be infinite. Okay? You will have to spend a lot of power, alright, to push the thing up to infinite. So the real op-amp will have a finite bandwidth. Okay? Alright? So now, we have this circuit where it's an inverting amplifier configuration, Z1, Z2. Now if we analyze it, right, with a real op-amp with a finite gain A, okay, we can do the same analysis, alright, but now you see a transfer function, A comes in already. Alright, why does A come in? It's because this input difference is V out divided by A. Okay? Remember, in the ideal op-amp, we assume that A was infinite, virtual ground, right? Here is ground, here also ground. But now, if I put a real gain here, right, it means that 0 minus V minus times A equals to V out. Okay? Now, please remember this, when you analyze this kind of circuit, please do not put virtual ground again, right? Because it's only valid for ideal op-amp, right? If you see a real A there, you have to analyze it like a real op-amp. Okay? Alright? That's why when you try and get the transfer function, A will always come in. Okay? Right? Right, so then now we can say, okay, for Z1, Z2, if you assume that it's a bilinear, okay, there'll be 1, 0, 1 pole. Okay? And now for our real op-amp, we will also assume that there's finite gain and also finite bandwidth. Okay? Right? So you ask me, okay, this expression for the real op-amp, right? Where is the gain? Anybody can tell me where is the gain? Where is the gain in this equation? What is omega u? What is this term here? This is the unity gain bandwidth, right? It's the unity gain bandwidth. Okay? So the gain is, okay, so what is it? What is the DC gain? Put S equals 0. Right? You put S equals 0, the gain is omega u divided by omega p. Okay? So the gain A0 is omega u divided by omega p. Right? So omega u is the unity gain bandwidth, omega p is the 3 dB bandwidth. So omega u is always bigger than omega p, which means there's a gain there. Okay? Right? Okay? So sometimes people also write differently. They just write, instead of omega u, they just put A0 or whatever. Right? A0 divided by S plus omega p. So it's the same thing. Okay? Right? So the gain A0 is omega u divided by omega p. Okay? Alright? Alright? So now if you go and do all this, right? Put all these things inside this equation, you will get quite a complicated equation now. For the transfer function of this simple inverting amplifier. Okay? With a real Z1, a real Z2, and a real op-amp. Okay? So you see, previously, remember when we analyze it and we assume a ideal op-amp, we had a bilinear transfer function, right? 1, 0, and 1 pole with some gain. Now, if you say my op-amp is not ideal anymore, it's a real op-amp with a finite minus 3 dB, finite gain. This is a transfer function. This is not bilinear anymore. You still have 1, 0 on top. Okay, that's okay. Okay? But now, your denominator is no longer first order, right? It's second order now. It's an S squared term here now. Okay? Okay? So you have, instead of 1 pole, you have 2 pole. Right? And why you have 2 pole is because you get 1 pole from the Z1, Z2 side, you have another pole from the op-amp. Okay? Alright? So you can see how the equation very quickly become complicated. Okay? So this is another reason why we need a computer simulator. Okay? Alright? Because human being cannot handle this kind of complexity. Right? Okay. So this is a numerical example. Alright? So if you put in the numbers and you just do all this scaling once again all over the place again, right? Okay, you see this become very complicated, right? Second order term. Okay? So now you see the two functions are slightly changed from previously. Okay? So previously 1, 0, 1 pole, and then you expect if ideal op-amp it will be flat. Okay? But now the real op-amp now got a second pole there. Right? So at high frequency, it will drop again. Okay? Right? The phase also, right? Initially, we expect to be flat, go up, and then flat again. right? Because the pole 0 at high frequency just cancel out, right? But now because your op-amp has a pole, it will drop even further. Okay? Okay? So you calculate all this, you get this 1 0. You have one pole, which is the original pole but slightly shifted a bit, and then this is the second pole. All right, second pole. Okay? Okay, so this basically says that if your op-amp gain is very high, okay, you can simplify it slightly. Okay, you can simplify it slightly. All right? And then if you assume that your op-amp not only got very high gain, but got very, very high bandwidth, all right, you get back to the ideal op-amp equation. All right, which is what you expect, right? All right. So remember, the ideal op-amp, we assume that gain is infinite, which means very high. Bandwidth is very high, infinite bandwidth. Right? We have this simple expression, right? 1 0 1 pole. Right? So now in our real op-amp, we got a complicated equation. If we apply back the simplifying assumption, right? What happens if the gain is very high? What happens if the bandwidth of the op-amp is very high? We should get back to the first one. Okay? So this why you say what is this thing useful? Yes, it's useful. Because when you analyze something with a real op-amp and you get a very complicated equation, how do you know whether it's correct? How do you know whether you not made a mistake somewhere? Okay? You apply this test. See, my final equation I got very complicated. If I now recheck it, right? Recheck my equation and say, okay, if I make the gain very high and I make the op-amp bandwidth very big, do I get back the simple ideal equation? If I get, that means chances are my equation, my analysis is correct, right? If I don't get back, that means somewhere along the line I made a mistake somewhere, you know? Okay, all right. Okay, so basically here is a summary of all the inverting amplifier. Depending on what you use for Z1 and Z2, all right, you will get different value of pole and 0, and you will get different value of the transfer function. Okay, so here you can see right here no 0, right? These two got no 0, only got 2 pole. Okay, right? This one no pole, only got 1 0. Okay, so depending on what we do for Z1, Z2, whether we put a resistor, a capacitor in parallel or in series, we will get different kind of response. And if, let's say like this case, right, where we put for the input, we have a resistor in series, a capacitor, but at the feedback, we have a capacitor in parallel with a resistor, actually you will end up with a more complicated equation. You will not get a bilinear, you will get a second order. That means the denominator is S squared. Okay? S squared. Okay? So this one is even if you assume an ideal op-amp. Okay? Alright? Okay, so you see special case, right? Input is resistor in series of capacitor. Feedback is capacitor in parallel with resistor. Okay? You end up with a second order, okay, in the denominator. Okay? Okay, so similarly, that was for inverting amplifier. Now we talk about non-inverting amplifier. Input apply to the positive input. Okay? Always, in this case for non-inverting amplifier, input always apply to the positive input. Why? 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 Because you want negative feedback, okay? Negative feedback. Okay? So all these circuit, remember, we are using negative feedback to stabilize. Okay? We never do positive feedback, okay? What happens when you do positive feedback? Whole thing is not stable anymore. Okay? All right? You don't believe, you go analyze it. Okay? All right? Positive feedback means small change in output will become added to the input. Add to the input, output will increase. Output increase some more, add back to the input, input will increase. Saturate, everything will just saturate, max out. Okay? It will not stabilize. Okay? You don't believe, you go to the lab and you go and hook up components. All right? If you connect wrongly and you get positive feedback, your circuit will not work. Okay? Either your circuit will just saturate to the power supply or ground, or if you're lucky, your circuit will oscillate, become like a clock. You know, high low, you know. Okay? Sometimes some designers they design, right, connect wrongly or whatever, right? Instead of an amplifier, they got a clock, you know, clock circuit. Okay, all right. Okay, so here is for the same analysis we do. Okay, op-amp is still a real op-amp with a finite A of S. Okay, but non-inverting. All right, that means apply input, the positive input, work out the transfer function. Okay, you will get this. Okay, all right. So now we can check. Okay. So in order to implement Z1 and Z2, which use only resistor and capacitor, okay, because for IC technology, right? Then the K factor, what is the K factor? K is your your DC gain is what? Of this transfer function? S equals 0 is your DC gain is K times omega Z divided by omega P. Okay? Alright? So the K is the additional gain scaling factor. Alright? Okay? So you cannot independently choose 3 parameters, alright? K, Z1, and Z2, because you may not be able to get the correct values for R and C that you can implement. Okay? Alright? So for example, if K is greater than 1, then this K omega 0 minus 1 must be greater than 0. Okay? If K cannot be less than 1, because otherwise the numerator is negative. Okay? Okay? What happens if the numerator is negative? You cannot realize the filter because there's no way of getting a negative capacitance. Okay? So sometimes when you analyze, right, in the mathematics you can get a negative C value. Right? It's possible. Right? In this case, right, if you choose K less than 1 and you solve this, you will get a negative C value. So mathematically it's possible, but you cannot implement because you cannot find a negative capacitance. Right? Or if you do, you get Nobel Prize. Okay? 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 And if you work it out so that KZ1 minus P1 is negative, that means you have the 0 located in the right half plane of the Laplace plot. Okay? So this one you all have to understand, right? The Laplace plot is real value, imaginary value. Okay? S can be a complex number. Okay? S can be a complex number. Real plus j omega. Okay? When we do the mapping of the Laplace transform to the Fourier transform, we say S is equal to j omega. That means S is along the vertical axis. Right? But the 0 can be anywhere in the expression. Okay? And if the 0 in the transfer function happen to be in the right half plane pole, we say is what? The filter is unstable. Why do we say that? Which means that if you take the inverse Laplace transform in the time domain, you will get an increasing exponential with time, e to the alpha t. Which means that the signal is increasing, keep increasing, right, to infinity. So it's not bounded, it's not stable. Okay? Okay, so this is the important concept of stability now. It just came out with stability. So when do you first encounter this concept of stability? When do you first encounter this? In your courses? Sorry? Op-amp. Where? When? Okay. So remember when you first design your op-amp or your first op-amp course, right? We always talk about the phase margin. All right? So stability comes in. Why? Because we always use the op-amp in a negative feedback configuration to stabilize things. Negative feedback, right? So negative feedback means output subtract at the input. Okay? Then you get the A divided by 1 plus A beta. Okay? Unfortunately, when the signal go through your op-amp, what happened to the phase? The phase is changing. Right? The phase is changing. Depending on the transfer function of the op-amp, right? Your signal go through op-amp, the phase is changing, and phase is dropping. Typically it's dropping. Right? So now you have a problem. If the signal go through your op-amp and the phase change by 180 degrees, then what happens? I apply feedback to subtract at the input, which means another 180 degrees. So now the total become 360 degrees. So when it becomes 360 degrees, what happens? My negative feedback becomes positive feedback. And my circuit becomes unstable. Okay? So that's why we need to study stability, because we have to ask ourselves the question, how stable is my circuit, my negative feedback circuit? That's why now when you design op-amp, right, we always ask, okay, what is the phase margin? And what's the definition of phase margin? What's the definition of phase margin? How you measure phase margin? How far away is the phase from 180 degrees? That's the phase margin. Right? So now you know what's the reason. Right? Because when it becomes 180 degrees, you're unstable straight away. So I want to know how much margin I have. Right? Because I know that if the phase becomes 180 degrees, feedback, I will get positive feedback. Alright? So I want the phase to be as far away from 180 degrees as possible. Right? And the measurement is the phase margin. Right? So typically people say what? Depending lah. Right? Some people say, okay, 45 degrees enough. People say, oh, maybe sometimes we need 60 degrees. Right? Sometimes say, oh, better still, 90 degrees better. Okay? Alright? And if you look at the analysis, you'll find that how big a phase margin you have will determine what's your time, your unit step response. Right? If your phase margin is too small, even though it's not 100 degrees, if it's too small, let's say 10 degree, 20 degree, 30 degree, right? Your step response may have a lot of ringing. Okay? I put a step in the input, I look at the output, right? It's ringing, oscillating, and then stable, and after a long time, then it's stabilized. Okay? Which is not good for some applications. Okay? So if my phase margin is 90 degrees, you find that it's quite clean, right? I put a step input, it will rise exponentially to the output, so it's quite clean. Okay, there's no ring. Okay? Okay. So now you know why we talk about stability, why you design op-amp, we always ask you what's the phase margin, and how is the phase margin measured? How is it measured? What is the phase when the gain is 1, right? When the gain is 1. Okay? Do you ever think why is defined like this? It's because you assume that the worst case is that I connect the op-amp in a unity gain. Right? Unity gain, right? Means I input go to the positive input, and then I take the output and connect to the negative input. So this is what we call unity gain. Right? That's why we check in this unity gain configuration, what is the phase margin to tell me how stable this thing is. Okay? So if I got good phase margin and unity gain, I don't worry. If the user used the op-amp in non-unity gain, right, the phase margin only get better. Okay? Okay. I think I'm going to speed up now. I still got quite a lot. Okay. Okay, so this one, I think you go back and look at yourself at this example, right? Basically, we are just going to redesign the bilinear filter, put a zero at a different place, okay? And we want a positive high frequency gain. Okay, that means we have to what? Zero before the pole, okay? Because we want the gain at high frequency, okay? Right? And we can choose different value of C, okay? Okay, so here, right, if this kind of circuit, we have this kind of gain, which is not good, so we need to correct for it. Okay, how to correct the gain? We apply this kind of resistor divider network. Okay, so this is still inverting amplifier configuration, except now the input, instead of going straight into the positive input, it goes through a scaling network. Okay. So this value at the input is RB divided by RA plus RB. Okay? Okay, so with this I can scale the K factor. Okay? Okay, so here with different connection and different, you can get different circuits. Okay? Right, this is the normal R2 over R1. Now the feedback, if I, instead of using one resistor, I use a parallel combination of a resistor capacitor, I will get a slightly different transfer function. Alright? And now, here, if I just replace this resistor by a simple capacitor, okay? I will, no more pole, just straight zero only. Okay? Okay, so what is the design procedure? Okay, first we will use the body plot straight line, right, to determine what are the break point, right? Where's the zero, where's the pole, all right? There'll be one. Once we know the position of zero and pole, we can write the transfer function, right? Because bilinear, right? Zero, S plus omega Z, S plus omega P multiplied by some gain function. Okay? Then we can determine what's the gain, pole, and zero location. Okay, select what type of circuit we want. Okay, op-amp, what is Z1, what is Z2, all right, and then go through the same process. Okay, first analyze it in a normalized domain, work out what is the component value, the normalized component value. All right, if you have too many parameters and not enough equations, you choose certain components. Okay, right? And then you work out the rest. After you get a normal component burden, you then do the scaling, okay? Both frequency and magnitude, all right? And then we do this thing called iteration, okay? So here I want to say a little bit thing about this iteration. This is a very important concept in design. Iteration. What is the meaning of this? You all know? Iteration. That means, first you try and solve it. You make some assumption, you solve the equations. Okay? Then you get one solution. Right? Then, if the solution is not near what you want, okay, you take this and you, again, solve it one more time. Right? So it's an iteration. Okay? And this concept actually comes from mathematics of a nonlinear equation. Okay, so you all know, right? If I give you a nonlinear equation, how do you solve it? How to solve nonlinear equations? Use a computer. Is it? No. So one way to solve a nonlinear equation is by iteration, right? That means I guess. I make a first guess, right? So if I give you let's say a fifth order polynomial, x to the 7 plus 5x to the 6, whatever, right? I ask you, okay, what is the solution to this 7th order polynomial? There's no equation you can use straight away, right? So what you can do is you can do a first guess, all right? So I guess maybe x is equal to plus 2 first, all right? And I put in, I calculate what is the function, right? Right? And then you solve, and then after I plug in again, right? And I keep iterating round. And if I'm lucky, the thing will converge. Okay? If you don't converge, that means you pick the wrong value at the beginning. Okay? Right? Okay? So if you have a non-linear equation, this is how you solve it, by iteration. Okay? So I think if you even look at all the textbook, they will tell you this iteration, I mean, they are basically trying to search for the zero crossing of this non-linear function. Okay? And there are different ways to get to this zero crossing, bisection and all this, yeah. Okay? But iteration is a common tool for non-linear equation, okay? Okay, so this example here, right? Okay? So if I give you this kind of a body plot, if I say, okay, this is a filter, I want this kind of filter, all right? The magnitude function looks like this. 0 dB, come down, start coming down, first breakpoint at 100 radian per second, okay? And then at 1K, it's flat. At 10K radian per second, it goes up, all right? At 10 to the 5, it is flat again. Okay? How to implement this? Okay, so first, we look and say, okay, flat, come down. It means one pole here. One pole here. All right? Then, after it drops, become flat. That means one more zero here. Okay? After it go up again, must be one more zero here. Okay? And then flat, one more pole here. So, looks like this is a 2-pole and 2-0 system. Alright? 2-pole, 2-0. Alright? So straight away we write, okay? Some gain factor, 2-0, 2-pole. Right? Then we plug in all these frequency breakpoint, right? To find out, okay, what is the zero and what is the pole. Okay? Alright? So if you want to implement this now, okay? We say, okay, what do we know? 2-0, 2-pole. Okay, we know each bilinear give me 1-0, 1-pole. That means if I put two bilinear together, I should get this, right? 2 bilinear, 2-0, 2-pole. Alright? Okay? So I just have put one bilinear here, one bilinear here. Okay? So I can use two inverting bilinear filter. Okay? Okay, then we do all this normalization and denormalization again, to pick out what is the R and C values I should use. Okay? Well, we're already 8:39. Okay. Right, so here is a summary of how we will design a filter. Okay? We start the filter spec. Okay? Pass band age, stop band age. What is the maximum ripple in the pass band? What is the minimum attenuation in the stop band? Okay? And then we'll get a transfer function, magnitude and phase. We can check for the group delay to see whether the group delay, what is the group delay looking like. Okay? Group delay basically is change of phase with respect to frequency. Okay? Then we can do some frequency scaling because we are working on normalized transfer function. And then we scale the component values later. Okay? So here we talk about two different types of first order filter, passive, active RC. You can use the table, right, to see what kind of response we need. Alright? And then we use the design methodology, okay, for the given transfer function and the pole zero location. Okay? For first order, very simple, right? 1, 0 and 1 pole. And then we have to consider what's the effect when my op-amp is not ideal. Alright? Okay? So the non-ideal op-amp would cause some slight shift in your result. Okay? And we look at what was the effect on the inverting and the non-inverting circuit. Okay, so here are some references if you're interested. Okay, you can see that there's an entire book on design analog filters. Okay, all right, entire book. Okay, so earliest version 1982. All right, updated 1981. Okay, so this guy is still alive, huh? Okay, so very quickly, let's try and go a bit quickly, see whether we can get. Okay, so now what about other type of filter different from the bilinear? Okay, so we talk about two different kinds. One we call the biquad filter, and then the second type of filter we call what we are called the maximally flat filter. All right, and the Butterworth is one special case of this maximally flat. Okay, what do we mean? We go through and say. Okay, so bilinear we mentioned, right? Numerator linear, denominator linear. Okay, 1, 0, 1 pole. Okay, biquad means higher order. So what happens if my numerator instead of first order becomes second order? All right, so if both sides, top and bottom, is second order, we call this the biquad transfer function. Okay, all right. So now S square on top, S square below. Okay, all right. Omega 0, so look at the parameters we have, right? We have K, different K values, we have omega 0, and then we have this thing Q, or the quality factor Q. Okay? Alright? So now this is a special case of a biquad where K1, K2 equals 0, K3 equals to 1. Alright? Okay? So this simplifies to this kind of circuit. Alright? R, inductor, capacitor. Alright? Input here, output taken from here. Alright? If you do the analysis for the transfer function, you will get this. Alright? LC, R, and then here, if you just simplify, if you make omega 0 equals to 1 L square LC, and then make omega 0 Q equals R over L, you simplify to this equation. So now Q is something which we call the quality factor. Okay? Quality factor. So the quality factor is a measure of the energy efficiency of this circuit. Okay? Right? Okay? Right? So you may hear people say that this is a high Q circuit, this is a low Q circuit. Okay? It's a measure of the energy efficiency. Okay? And we mentioned that inductor is hard, high Q inductor is hard to implement on a chip. Okay? So the inductor on a chip is low Q, okay? Means that the energy storage is not very good, not very high. Okay? So now if you once again, this is a transfer function of a biquad, simplified biquad. Okay? If you look at the transfer function, you see that, depending on the different value of Q, you see the biquad, there's a big overshoot and then coming down. Okay? And how high is this peak? Depend on the Q. The higher the Q, the higher this peak is. Okay? Alright? Okay? You can see, right? If you take this equation, take the magnitude, that means do J omega, and you take the magnitude, right? For DC, omega equals 0, everything, the transfer function magnitude is 1. So here, DC is 1. Okay? At very high frequency, S omega equals infinity, this goes to 0. So high frequency goes to 0. And then what happens at exactly at omega 0 is equal to the value of Q. Okay? Alright? Okay? So similarly for the phase, depending on what's the value of Q, the phase transition is also different. Okay? Right? So the bigger value of Q, the sharper is the transition. Okay? Okay? So here is talking about the different location of the pole. Okay? So in this simplification, there's only 2 poles. Okay? There's no 0. This biquad only in the denominator, so there's only 2 poles. Okay? And the location of the 2 poles, okay, will depend on omega, will depend on Q. Okay? Right? And omega 0. Okay? Okay, so for different Q or for different omega 0, you can see how the different pole is changing. Okay? And also the filter response. Okay, so how do we actually implement this biquad? So previously we talked about bilinear, how to implement Z1, Z2, okay, can be resistor, capacitor. This is how we implement a bilinear. Now, for the biquad, okay, we will write again transfer function in the normalized domain, okay. Here is the second order, okay. So we rewrite all this, okay, and then we can see that this become like a 2 first order multiplied by integrator, okay. So mathematically we take from here, we can map it to here, okay. See, 2 first order here multiplied by the integrator, right? So this equation can be redrawn as a circuit like this. Okay? And then we can go and map each of these blocks into an actual circuit. Okay? Right? So integrator we know, right? R and C become an integrator. So this becomes the integrator. This multiplied by -1 is a simple inverting amplifier. Okay? And then these two linear block implement like this. Okay? Right? So now you see this transfer function become like this. Okay? So now you have how many unknown? 1, 2, 3, 4. You have 5 resistors. Okay? 5 resistors. How many capacitor? 1, 2 capacitor. Okay? So obviously you have a lot of unknowns. Alright? You only have a few equations. So you have to do the same trick now. Okay? We fix certain values and then use the known equation to go and derive the rest of the values. Okay? Okay, so you got 6 components, right? 6 unknown. Alright? You have only three performance values, omega 0, Q, and H. Okay, so arbitrary choice, you just choose any 3 and then work out the other 3. Okay? Alright? And then we say, okay, we do what we call tuning. Tuning means adjusting. Okay? How do we adjust all these values? Alright? Now, we cannot anyhow tune because some of these component value affect more than one parameter. Okay? So when we want to tune or want to change omega 0, change Q and change Q or change H, right? We have to tune it by choosing values which will not affect the rest. Okay, so this is what I mean by orthogonal tuning. That means if I want to change omega 0, I just change R2. Right? If I want to change Q, I will just change R1. I want to change H, I just choose R3. Okay? In this way, my tuning will be very smooth. Right? If I don't do like this, I may have to do iteration. Alright? I go and change omega 0 by using, let's say, R3 or R1. Alright? Then I tune Q, I change R1 again. Then I got to go back and change omega 0 again. So, you know, it's not orthogonal. Okay? Okay, so this is one example of the biquad. Okay? Let's say I want the -3 dB to be 22 kilohertz. I want the Q to be 0.707. I want the DC gain to be 6 dB. Okay? So all this the solution will tell you how to go and pick all these values, right? Okay? We have to move on because I think time is quite tight. Okay, I want to go on to the Butterworth side. Okay, and then once you pick these values, you can implement, for example, and then if you use MATLAB or whatever, right, you will find that this is the curve, all right, or the magnitude and on the phase, all right. Okay, and then we can do the same thing, right? If you want to have instead of a low pass, a band pass, okay, we just pick the output from a different point. Okay, that's the beauty of it, right? Low pass we pick from here. If you pick from V2 prime, you'll end up with a band pass circuit, okay? So you see the magnetic response is passing this band, okay? So there's a 3 dB from here to here, all right? And this is what we call the band pass, okay? So here is an example, okay, of a band pass, how to design a band pass filter. I want the band pass center, omega 0 to be 1 megahertz. I want the bandwidth to be 200 kilohertz. The peak gain is unity, okay? So you apply all the equations, you get all these values, okay? And then you pick all the value, and then now you do MATLAB or simulation, SPICE simulation. You see, yeah, here, magnetic response, you see, band pass with a certain bandwidth, okay? Okay, these are other types of biquad filters, okay? Depending on what's all these values, you have different low pass with peaking, band pass. Here is a band stop filter. Here is a high pass with peaking. And here is an interesting case of an all pass filter. All pass. Magnitude, everything pass. But the phase is being adjusted. Okay? Alright? So here is the same thing, information. Okay, so now we want to go to this important part of filters, maximally flat. Okay, and this will appear in your homework. Okay, so very important. I need to cover this. Okay? So, what is a maximally flat response and what are Butterworth filters? Okay, so here is the example of an ideal filter. Okay, ideal filter. Very sharp edge. Okay, pass band, stop band. Zero transition point. This is what I call like a brick wall filter. Okay, right? Real circuit cannot be like this. So real circuit will be like this. Transition from pass band to stop band. Okay? So we will have this is the frequency response. Alright? And then we will try to get a S domain transfer function. Okay? So that we can implement the filter. Okay? From the transfer function. Okay? So this is roughly what we want to do. So if you work out what is the magnetic response, okay, assume that this is the S domain, alright, and then this will be the frequency domain j omega, okay, you find that this magnetic response basically is like numerator, denominator, okay, then now, for the numerator, okay, if we, sorry, what is this? Okay. This is the, sorry, n is not numerator. N is the magnetic response, okay? So now in the magnetic response, this is a general case, all right, where n is the order of the filter. Now, if we say it's a special case where the numerator of your magnetic response is 1, and the numerator is of this form, okay, 1 plus B2 omega squared plus B4 omega plus B2n omega 2n. That means I only have 1 0, and the 0 is the infinity, that's why it disappears. And I only have all poles. Okay? Okay? Then now I can define this as a characteristic function. Okay? Alright? Like this. And if I want it to be as flat as possible, alright, if I want it to be flat as possible, which means that mathematically, I know that if all my derivative, okay, is equal to 0, I will get a very thing which is very flat. Okay? Alright? Okay? So if this is the case, right, if I can write the magnetic response in this form, 1 divided by 1 plus epsilon squared times omega n to the 2n, alright, I will get a very flat response in my pass band. Okay, and this flat response is what we call maximally flat. Okay. So here you see, right? If this is my so-called maximally flat filter, which we should now define as a Butterworth, okay? You see at the pass band is very, very flat. Okay, it's very, very flat, and then it starts to drop off. Okay? Now, what are all these? These are the different order of the filter. Okay? N equals 1 first order, that means like this, very big transition region. As I increase the order of the filter, the transition region becomes smaller and smaller, becomes sharper and sharper. Okay? You see, this is when 10 order, you get this. Okay? Right? So you see, for this kind of a maximally flat filter, which we call a Butterworth filter, when epsilon equals 1. So here, epsilon equals 1. That means the magnitude transfer function is 1 divided by 1 plus 1 times omega n to the 2n. Okay? You see? Epsilon equals 1. So this special case of a maximally flat filter we call the Butterworth filter. And what is the special characteristic of the Butterworth filter is that when omega equals omega n, what happened? They all pass through this point. Okay? Okay, which is the 1 over square root 2 point. So I don't care whether it's a first order, second order, third order, fourth order, fifth order, sixth order Butterworth filter. When omega equals omega n, it will all pass by this point, okay? Which is the 1 over square root 2 point. Okay? All right? Okay, so here is all the equation regarding where the pole of all this Butterworth filter is. Okay, so all the pole actually all end up in the S domain, end up in the unit circle. Okay, right? So but we only choose the pole on the left half plane because it has to be stable. Okay, has to be stable. Okay. So we drop all the pole in the right half plane because we know that this is not stable. Okay? Okay. So, good thing is that because the Butterworth function is very well known, okay, there are a lot of tables to help you design the Butterworth filter. Okay? Right? So you see all these tables you can find in all the textbook. Okay? For different Butterworth filter order, n equals 2 or 3 or 4 or 5 all the way to 10, they really tell you where should all the pole be. Okay? Right? So if n equals second order, there should be 2 pole, and they are at minus 0.7 something, plus minus j this. Okay? So all the poles are in the left half plane because it has to be stable. Okay? Right? Okay? So this is where the pole or the Butterworth filter is. This table tells you what is the coefficient of the Butterworth polynomial. Alright? Okay? Remember the Butterworth polynomial is 1 plus something, blah, 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 right? Okay? So if n equals 2, it's 1 plus a1s. Okay? If n equals 3, is 1 plus a1 is 2, and then a3 is 2 also. Okay? Alright? So here is the Butterworth function, right? Is s to the n plus some polynomial in ai si. Okay? Okay? So the highest power of Sn is always 1. Okay? Okay? Other table tell you, right? What is the Q on the Butterworth filter, right? Okay, so here is a very important example, okay? So for example, all right, you are given a certain filter characteristic you want to implement, right? That means I want to implement a low-pass filter with a cutoff, right? FP cutoff at 20 kilohertz, all right? Here's FP, and then That means the FP is like the passband edge. And then I want to have the stop band, starting at the stop band edge at Fs. Okay? Passband edge, stop band edge. Okay? And I only allow minus 20 dB maximum deviation, right? Or ripple at the passband. And I want a maximum attenuation or minimum attenuation, right? At the stop band. Okay? What kind of butterworth filter do I need, right, to meet all this spec? Okay, that means I need to find the order of the filter, right? Because here you can see, right, from the passband edge to the stop band edge, there's a transition. So I define what is the transition region of the filter. Okay, and we know that from the previous plot, right, the sharper the transition, the higher the filter order that's needed. Okay. Right, so with this, we should have the information we need to find what is the Butterworth transfer function we need and what's the order. Okay? Right, so basically we start right? We know that this is the magnitude function of the Butterworth filter, right? Basically, right? Very simple, Omega n order times 2 to the n. Okay? So now, if we know that the maximum ripple is this, all right, we can calculate what's the n. Okay? Okay, because we know what is the passband edge, all right, and we know what is the stop band starting. Okay, and we know what is the alpha values, the ripple here and there. Okay? So with this equation, all right, we can calculate what is the n, all right, and then we have to go to the nearest integer, okay, because the filter order is integer, okay. Okay, so you calculate this is 3.33. That means the order you need is 4. Okay, you must round up, don't round down. You must round up. Okay. All right, and then once you know that you need n equals 4, then you just go to the table and find out what are the coefficient values of the Butterworth transfer function. Okay, right? Okay, so this is the first example, right? First example where at the 3 dB point, the value is 1. Okay, so this is 3 dB and it's 1. Okay? Okay? See, so for two different cases, right? The passband ripple, two different cases, right? One case is 3 dB. 3 dB, we know is a Butterworth filter. Second case is not 3 dB at omega pn. Okay? It's only 0.5 dB. So now in this case, it's not a Butterworth filter, right? Because Butterworth filter says that omega pn equals 1, this has to be 3 dB. But now it's only 0.5. Okay? But we know that it still has maximally flat response. Okay? So we use the more general equation where you have epsilon square. Okay? So now we replug in the equation, all right, with epsilon defined by 0.5 dB. Okay? And you can calculate. So now the order becomes 4.83. So round up becomes 5. So now the order has increased from 4 to 5. Okay? Okay. So now how do we find the coefficients? Okay, we cannot use the table for Butterworth because it's not a Butterworth filter. Okay? So here now we will do a simple smart trick. Okay? So engineers are very good at tricks, okay? Okay. So basically we know that it's a maximally flat response, so it's this equation with epsilon. Alright? And then we do some substitution. Alright? Where we define omega d to be epsilon 1 over n times omega n. Okay? So we do this substitution, to transform this transfer function, which is not Butterworth, to a new transfer function, which is Butterworth, but now with some frequency substitution. Okay? And this is the frequency substitution. Right? So now we get to this. It looks like a Butterworth transfer function again. Right? Remember, n is now 5, right? So this is some sort of what we call denormalization now, right? So now we come to this, then we can go back to the table again, right? Go back to the table, all right? To say n equals to 5, what is the Butterworth coefficient? Is this normalized to S of D, all right? Then from this, we can break it up, all right, to a single order, first order, and 2 biquad. Okay? Okay, then from that we can now implement, okay, using a known circuit which we call the Sallen-Key circuit. Okay, right? So the Sallen-Key circuit will give you a transfer function which is a biquad, S squared. Okay, so that's why we break this up. This fifth order we break up into 2 S square and 1 SD. Okay, because we know that in the Sallen-Key we can implement S square. Okay, so if you plug in, right, we plug in the Sallen-Key, plug in all the values, we can choose again, once again, all these capacitor and resistor values. Okay, so this will be the final circuit. Okay, and you do MATLAB, this will be the magnitude transfer function. Okay, so that was for the Butterworth, and we can do the same thing for the maximally flat, right, for 0.5 dB. Okay, and you can work out again all the values. Okay, so now this is the complete value circuit implementation of the 0.5 dB passband edge case. Here are the 2 S square terms which we implement using Sallen-Key. And then remember, we had one first order term we will implement using like this. And then this is the first cascade. And then here is the frequency response. Okay? Okay, so here is roughly is the design flow. All right, we start off with frequency response. We try and find what is the S domain, normalize, okay, and then we will synthesize, okay, using the Butterworth. If we do some frequency tricks, and then from the Butterworth polynomial, we will implement using S square polynomials using the Sallen-Key circuit. Okay. Okay, today is quite a lot now, so because we combine two lecture into one. Okay, so basically we talk about biquad filters, second half biquad filters, biquad transfer function. We can implement using 3 op-amps. All right, there are 6 unknowns and 3 design equations, so we just choose 3 values and then we find the other 3. And then we talk about maximally flat response. Okay, and what's the transfer function? How to use tables. All right. And then how to implement using the Butterworth filter, and how to implement Butterworth filter using the Sallen-Key circuit. Okay, so the design methodology again, 3 design equation and 1 more for gain adjustment. Okay, and then here is the important class of filter requirement. When the passband edge is not at minus 3 dB, because at 3 dB, minus 3 dB is Butterworth, but if it's not at minus 3 dB, let's say at the passband edge is only 0.5 dB, whatever, minus 0.5 dB, then we have to go and use the maximally flat equation, all right, to derive what is the filter order, and then do the frequency substitution trick to get to the Butterworth transfer function, okay, all right, and then design it using the Butterworth filter tables, right, and then we scale back the frequency back to a specified value, okay. Okay, so give me 5 more minutes. I just want to share with you the homework, which you will have 2 weeks to do. Okay, where is it? Okay, it's under here. Okay, so this is the one. Okay, so this is the very first homework, right, for this class. Or Professor Hing also submitted one, is it? This is the first one. Okay. So Professor Hing one, he will inform, right, when he comes back, when it's due. Okay. So this homework has got total of 3 questions. Okay, right. First one is on first order dialectic modulator. Okay. Please refer to slide 44 of the lecture 7 notes. Okay? Sorry? Okay, I mean, I keep the lecture number the same lah. So part 2 starts with lecture 7 lah. Okay, so because every year is part 1. Part 1 is from lecture 1 to 6. Part 2 is lecture 7 to 12. Okay, so this year because of Professor Heng being sick, we have to juggle the sequence, but I don't want to change the lecture number because next year he's not sick every year, right? So next year it will be lecture 7. Okay. So first I will tell you, these 2 question 1, question 2 are from last year's final exam. Okay. This question 1, question 2 is from last year's final exam. That's why I want to put in the homework. You all do. I'll give the solution. Right. So it help you to see, right, the last year final exam also. So I don't have to go through again last year final exam. Okay. That's why it's not so easy. Right? It's not so easy, okay? But this will give you a taste, right? Right? But you can refer to slide 44. The equation should be there. All right? Okay? Question 2 is quite challenging. Okay? All right? It's quite challenging. Okay? But it's something that this part you should see from the first order. Okay? One integrator. Except that the quantizer now has got multiple bits. Okay? Alright, so the quantizer has got B bits. And then we take the MSB to feedback. Right? And we take the non-MSB to go through this circuit. And then here we combine to get the output. Okay? Alright? So I ask you first to draw the linearized diagram again. Alright, you know what's the meaning of linearized, right? You look at the previous lecture slide. It's a linear circuit, right? E1 plus Q whatever, right? E1 plus X whatever got to Y. So now you do the same thing. The only tricky part is that you need to how to do this properly lah. Okay? So here I give you the hint. Okay? If the output of the quantizer here is W, alright, then W equals to E1 MSB plus E2. Okay? Alright? So with this, you should be able to derive the noise transfer function. All right? And I ask you what is the optimum value of G. Okay? And then part C again, please refer to slide 44 of lecture 7. All right? We'll find what is the optimum value of the SQNR. Okay? Here you assume that what is the optimum value of G you found from here, and you can assume that you have an ideal brick wall filter. Okay? And then part D, you just comment on the potential limitations of this architecture. So this one, please look at the slide I added to the lecture 7 on the mesh architecture. Okay? The clue is in there. Okay? And then the third question basically is on a filter. Right? It's on a filter. Alright? Okay? So here you can see straight away at omega P, right? Passband H, the value only 1 dB. Okay? 1 dB, so it's not a straightforward Butterworth. Okay? So the example was for 2 cases, Butterworth, where the passband H was at 3 dB. Second case was, an example, was a non-Butterworth because the passband age was at 0.5. So now here I just modify slightly to, instead of 0.5, 1 dB. Okay? So you should still be able to use the example, just adjust. Instead of 0.5 is 1 dB. Okay? So find again what is the required filter order n, and what is the magnitude transfer function, and then derive what is the Butterworth transfer function. Okay? Right? And then you just derive what's the scaling factor. Right? The scaling factor is the one that translates the non-Butterworth polynomial to the Butterworth polynomial. Okay? I don't even ask you to go and implement using salient key. No need. Okay? Once you can get the Butterworth transfer function, it's good enough. Okay? And then you tell me what's the scaling factor. Okay? All right? So if you have any further questions on the homework, please send me an email. All right? Normally I'll answer the email. All right? And normally I'll put the announcement so that everybody in the class, in case you have the same question, right, you will see the same answer. Okay? All right? Okay, so that's one good thing. If you have a question, please ask me, because another of your classmates may also have the same question you didn't ask yet. Huh? I will put the answer into Luminous as part of the announcement. As part of the announcement. Okay? All right? So I've done this in the previous classes. I think that's the best way. Right? Right? So I don't have to keep answering the same question. You know, you ask this question, answer you. Then you ask, answer you. So once somebody asks me a question, I assume that it's interesting to a lot of people. Then I will just answer and put it in. I may answer you personally, but I make sure I also post it on the Luminous announcement. Okay. So homework is e-submission. So please go to the. You all know, right? Please go to. Please go to homework submission in Luminous, all right? And then you will see all this, right? So these were all set by Professor Heng. I think he will adjust it. You just go to this one. This folder, right? This folder will close at 7 February at 11:59. Okay, all right. So just do your homework and then just submit there. Okay. So remember what I told you. I only have 3 homework or 3 tutorial. If you do and submit, all right, I will give you credit. And then out of these 3, end of term, I will pick one, okay, and I'll mark that one, okay? And that one will count. The one that I picked will count for 6%. The other 2, you submit something, I'll give you 2%. So total 10%. Okay? But I will not tell you which one I'm marking, okay, until end of term. Okay? Okay, any question? Okay, no question. Have a happy Chinese New Year for those of you who are celebrating. Okay? And then we will meet back again on 7th of February, unless Professor Heng is well enough. Okay? So he told me his MC is until maybe February something, I think, February 12 or something. What happened to him, is it? I don't know also. I don't think it's COVID. I don't think it's COVID. He's not so old. He's quite, right? I don't think so. But honestly, I don't know. He just told me he's hospitalized in medical leave. Right? And I don't want to probe too deeply. What's your medical condition? Tell me. Right? So he's not well. But I think he'll recover in a few weeks' time. Okay. So that's why I think the workshop and the homework one, everything will be postponed. Okay. But important thing, so the workshop, please go through and try to see whether you can understand how to use the cadence. You all have access, right? You all have access. Can you access cadence now? Yeah. Okay. So try and use it. You got a problem, please send email. We'll try to answer you. Okay. All right. Happy New Year. Okay. Happy New Year. 恭喜發財. Okay.